take a seat.
Ve Farnboroughu je možné se dostat i na taková místa, kam se běžný člověk nedostane. Teď sedím na pilotním místě Airbusu A-380.
This is MSN-1, the first aircraft to take to the air back in 2005. Here is the cockpit layout. So pilots of Airbus aircraft will feel immediately at home in here because we have a common cockpit philosophy. Some of the highlights are the vertical navigation facility because we have much taller displays. We also have the onboard information system where the pilots here can access all sorts of performance information, airport charts and so on. And also in here we can interact with all of the displays with the cursor control device, so they can change their flight plan actually on the screens. So we have a common cockpit, but we evolve all the time, each new aircraft, in order to bring the latest technological advancements to the flight crew. So the A380 is one of the first large aircraft flying that has electro-hydraulic actuation. And what it means in terms of benefit for the aircraft is that you can reduce the number of hydraulic circuits. The green and the yellow hydraulic circuit, and typically in most aircraft that are flying today, in large aircraft, like the 747, they have 4 hydraulic circuits. So this adds complexity and weight, and we've eliminated that by having the electro-hydraulic backup. And it also means that there's increased redundancy, and it's much lighter weight, so it saves about 1 ton of weight from the aircraft, which obviously reduces fuel burn as well and increases the efficiency. A lot of people ask, why do you keep a flight test aircraft in this configuration? And it's part of the continuous evolution that we do on all of our products. And we need an aircraft to be able to test these evolutions and the innovation that's continuously being brought onto the aircraft. So one example is the increase in range. We increased the range of the aircraft of the A380 by 500 miles by increasing the maximum takeoff weight, and we had to do the testing for that. So that's why it's very useful for us to have this aircraft here in order to do that testing. So it first flew in 2005, but we've kept it and we'll keep it into the future in order to continuously evolve the product. I mean, a product life cycle of an aircraft of this or any large transport aircraft is typically up to 30 years or even longer. The 747, for instance, the main competitor, has been flying for more than 40 years. So this aircraft will do so too, and it will evolve over time depending on the competitive environment, and that's why we need to keep on putting new technology inside and keeping the aircraft up to date. So this is the main deck of the A380. So you can see the volume that we have here. The width of the aircraft is about 50 centimeters wider than the 747 on the main deck, and that allows us to have 18-inch wide seats, which is comfortable, our long-haul standard, and that is given directly to the passenger. Of course, the airlines can configure the aircraft how they like, but generally you have economy class from here all the way up pretty much to the front of the aircraft, divided into cabin zones, and then obviously you have on the real aircraft, on passenger aircraft, the bins and the lighting systems to enhance the passenger experience. In terms of technology, you can see the floor beams of the upper deck are made out of carbon fiber, and in fact behind us as well, if it's possible to see through the netting, we have the rear pressure bulkhead, and this is a one-piece monolithic carbon fiber construction, and in total on the A380 we have 25% content by weight of carbon fiber. So this allows a weight saving of around 15 tons compared to using conventional materials. So this is done obviously to reduce fuel burn and to have the lowest cost of any wide-body aircraft per seat. Of course we're using to a certain extent aluminium, and also on the upper shells of the A380 it's a material called glare, which is a glass fiber aluminium laminate, which essentially is more corrosion resistant and more robust than aluminium. On the lower decks it is aluminium, but we use laser beam welding, so it's a slightly different construction from aircraft to date, which also reduces corrosion and therefore maintenance costs. Titanium is also a large part, a significant part, but that's mainly on the landing gears. The main landing gear and the nose landing gear are made of titanium. So there you have more or less the primary constituent elements of the aircraft. Spec empty weight without any equipment, it's around 240 tons. The max takeoff weight, then you have to put the seats and the cabin installation and so on. You add fuel, you add passengers and payload, and then the max takeoff weight is up to 575 tons. And this allows airlines to fly very long distances, up to 8,000 miles, 8,500 miles. And routes that are taking advantage of this are like from Dubai to Los Angeles. And Qantas recently announced the longest route in the world, which is from Brisbane to Dallas-Fort Worth. So this is the longest route in the world, and they will be flying it by the end of the year with their A380s. So if you want to keep cool at Farnborough, the best way to do it is just next to the air inlet from the preconditioned air. On a flight test aircraft, the way we distinguish what's flight test equipment and what's normal equipment on the aircraft is by coloring it orange. So on the ground here we have a lot of cables, and in total we have around 500 kilometers of wiring on the aircraft, and around 200 of this is for the flight test equipment. So this is actually bringing together all of the data. So we have 5,000 parameters that are measured. So this is temperatures, pressures, loads on the fuselage of the aircraft, are all collected and sent to the data storage units and also to the flight test engineer station. So they can control the flight test of the aircraft depending on what they're doing. And you can see also around the aircraft that everything in orange is related to flight test. And if you take that out, then you add the interior, then you have a passenger aircraft. In a normal aircraft there are around 300 kilometers of cables, so this is obviously for the avionics, for the electricity to pass through, and so on and so forth. So that's basically connecting all points of the aircraft, so all the way from the tips of the tail to the end of the aircraft into the cockpit as well. And during the flight test there's also a portion of this data which is transmitted live back to Toulouse to a telemetry room where engineers on the ground can also monitor the flight in parallel. So this station here is the flight test engineer station, and this is where the flight test engineers will actually manage the whole of the flight. So these guys will actually tell the pilots and which trajectory they have to fly, altitude, speeds, which is outlined in the flight test document. So they will actually follow these instructions, and then they will be able to monitor on all of these screens all of the parameters related to the test. So here you can see all of the data. They actually have a view also of the pilots in the cockpit. They have a view of the external aspects of the aircraft. We have external cameras all around the aircraft, so they can actually monitor everything, including the data coming in to this station. Fundamentally, when you first fly the aircraft on that first flight, they're really seeing a very small part of the flight envelope. So then steadily over the course of the flight test, they expand, what they say, expanding the flight envelope, which means they go up to the maximum altitudes, they go in terms of speed regime right to the stall, all the way up to the max operating and also doing the flutter testing. So slowly during the course of a flight test, the characteristics of the aircraft become very well understood, and then this is processed and programmed into the fly-by-wire system in order then to deliver the aircraft to the line, where line pilots are able to fly it, and it's also tuned to handle like any other Airbus in the fly-by-wire line.
We have the 970, the 972, the bigger brother, 80,000 pounds of thrust in the Trent.